Warm welcome to all my dear friends and students. A very good morning, good afternoon, good evening to all of you. And this is the DADM 1 lecture series, which is data analysis and decision making lecture series under the NPTEL MOOC. And we are on the 21st lecture. And if you know, which I keep repeating before I start the class, is basically this is a 12 weeks program, 30 hours total, and the total number of lectures would be of 16 number, each week having 5 lectures and each lecture being for half an hour. So, if this is the 21st lecture, that means we have finished 4 week and we are going to start for the 5th week first class, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we are discussing about hypothesis testing, and also you do remember that at the beginning of the 20th lecture, I did not show any slide for the first 10-15 minutes. I discussed again, repeated what was the plan of the hypothesis testing. So, I will not repeat it again, but wherever necessary I will highlight those facts. So, for the hypothesis testing, generally for the last 2 sets was basically where you want to find out something to do with the variance of the standard deviation of the population, provided in case 1 the mean values for both the distributions of the populations are known, and in the second case 2 the mean values for both the populations are unknown. So, we will consider we want to find out some relationship between the ratios of sigma 1 square to sigma 2 square, provided case 1 mu 1 mu 2 known and case 2 mu 1 mu 2 unknown. So, this is the statistical inference hypothesis testing for the variance, and the ratio is basically, as I said, is sigma 1 square divided by sigma 2 square, provided mu 1 and mu 2 are known. So, obviously, there can be 3 variants of each case, as I have been discussing. So, actually the hypothesis H naught is sigma is equal to sigma naught versus the case H A, which is the alternative hypothesis. Mu is equal to mu A, sigma is equal to sigma A, and sigma is less than sigma naught or the less than type. So, first let me draw the diagram, mark the nomenclature, and then come back to the rule. So, we will see the rules which you are stating are exactly as per the norm which you have been following time after time. So, this is, say for example, the F distribution, and this is the F value. Now, the F value would basically have 2 degrees of freedom, the sample size or degrees of freedom corresponding to the first set of observations from the first population, and the other degree of freedom would basically be the set of observations, the first set of observation from the second population. So, this is m comma n, and the ratio would be m would be in the numerator and n in the denominator, which I did discuss how the F distribution were being formulated. Now comes again the important part, and this is the repetition which I keep saying time and again in order to make things clear. So, the overall area onto the left hand side is alpha, the right hand side is 1 minus alpha. So, corresponding to that, this will be 1 minus alpha. So, this area is this. So, exactly matches what we have said. So, the ratio of the best estimates for sigma 1 square divided by sigma 2 square. So, what is that? Sigma 1 square best estimate is S dash square suffix m, because m is the sample size, and this is S dash because mu 1 is known. So, we are not losing any degrees of freedom. So, this is the case. I will not highlight, but I will just hover my electronic pen over this point. So, it is S dash square suffix m, and in the denominator what we had actually want to find out, the hypothesis testing was based on sigma 2 square. So, its best estimate from population number 2 would be S dash square suffix n, because n is now the sample size which we are picking up from population 2, which is again true. Now, as it is less than type, because sigma A is less than sigma naught, so hence it would be less than the particular value, critical value of f, where f would have a degree of freedom of n comma n, and it would be 1 minus alpha corresponding to the fact that what is the area to be covered onto the right hand side. So, the diagram we have done, the nomenclature we are following, it exactly matching with the rule or vice versa, whichever you discuss. Now, let us go to the second case under this. Here again we want to find out something to do with the ratios, and provided mu 1 and mu 2 are known, but here the hypothesis is stated as below. H naught, under H naught sigma is equal to sigma naught, and under H A sigma is equal to sigma A, but in this case sigma A is greater than sigma naught, hence it is a greater than type. So, this would be F distribution, again M comma N, the area onto the right as I mentioned is alpha, area onto the left is 1 minus alpha, and the area covered here is 1 minus alpha. So, this would basically be alpha onto the right. So, let us verify. So, if the ratio of S dash square suffix m divided by S dash square suffix n, so this is the case, is greater than type. So, obviously, it would be on the right hand side, is greater than f m comma n comma alpha. So, which you see is right. So, the nomenclature as stated as being followed is exactly matching the rule of rejection of H naught or vice versa. Now, let us come to the third case for the ratios of sigma 1 square to sigma 2 square, provided mu 1 and mu 2 are known, which are the population mean values for population 1, population 2. But in this case the hypothesis has been framed like under H naught sigma is equal to sigma naught, under H A here under H A obviously it will be sigma A, but in this case rather than less than type or the greater than type, we will frame it as not equal to. So, if it is not equal to, there is a probability that it will be both on the left hand side and the right hand side. So, first let us mark the diagram. This is F distribution as usual, F m comma n, F m comma n. Now, the areas to be covered now are equally distributed corresponding to the fact that the overall area in between this so called upper and lower control limits would be exactly equal to 1 minus alpha, which is the level of significance. So, if you are considering the area onto the left and the right are equally divided, so hence the area onto the right is alpha by 2. Area onto the left is alpha by 2. So, the area inside is 1 minus alpha as I mentioned it. So, the lower control limits, okay, I have not written the alpha values. So, let me write it down. So, it will become, so in this case total area to be covered onto the right would be 1 minus alpha by 2. As rightly pointed out here. So, it is less than, and area covered onto the right is again alpha by 2 and rightly pointed out here. So, in this case the statistic would be such that you will reject the H naught provided that ratio of the standard error square, that is S dash and S dash from both the case, because mu 1 mu 2 are known, if that ratio is less than for f m comma n comma 1 minus alpha by 2 or greater than f m comma n comma alpha by 2. So, this m n alpha by 2 1 minus alpha by 2 all are in the suffix in order to basically tell that for the F distribution what are the degrees of freedom and what is the level of or so called confidence level we want to put. So, here again the diagram, the nomenclature matches with the rule or vice versa. So, we are basically corroborating the fact time and again that how we are going to basically mention that in our drawing, in our concepts, and how the rule has been framed. Based on that we are proceeding. Now, I have not drawn it, but I will basically highlight it accordingly. So, this is the statistical inference based on the fact that you want to find out something to do with sigma 1 square with respect to sigma 2 square, provided mu1 and mu2 are unknown, and they would be 3 cases. So, what are the cases? I will repeat it first. In the first case, the hypothesis is H naught, under H naught sigma is equal to sigma naught, and the alternative hypothesis H A is sigma is equal to sigma A and sigma is less than sigma naught. That is the first case. Second one would be again same thing, under H naught sigma is equal to sigma naught versus the case of H A. Under H A you have basically sigma is equal to sigma A, but in this case sigma is of greater than sigma naught. The third rule being exactly the extension as we have been doing, under H naught sigma is equal to sigma naught and under H A sigma is equal to sigma A, but this sigma A is not equal to sigma naught. So, it can be of the less than type or greater than type. Point 1 is taken care, and I am sure I have understood. We also mentioned in this rule that mu1 and mu2 are unknown. So, if they are unknown, what is the case? We will replace them by the best estimate, which is x bar m, that is the sample mean for the first population where the sample size is of m size, and x bar n is the sample mean which is the best estimate for mu2 provided we have taken up a sample of size n. Now, if that is the case, obviously the corresponding standard error squares, both which are the best predictors for sigma 1 square and sigma 2 square. So, hence S, the S we will be using both for population 1 and population 2 as the best estimate for the variance square of the population would be S without the dash, because you are losing 1 degrees of freedom. So, in this case it will be S square suffix m and S square suffix n. Now, if you bring into the picture, obviously that F distribution would the degrees of freedom, the F distribution would also change. So, in this case it will be F m minus 1 because you are losing 1 degree of freedom from the first population, comma n minus 1 because you are losing another degrees of freedom from the second population, and it will be the suffixes apart from m minus 1 and n minus 1, it will be 1 minus alpha by 2 and alpha by 2 depending on which side of the test are you trying to look at. So, I will basically pinpoint the f values in the diagram and you will understand. In the first case, f distribution, this would be f, the value, this is alpha, this is 1 minus alpha, this would be f m minus 1, first degree is being lost in the first population, m n minus 1, and if you follow the nomenclature, the area on to the right is 1 minus alpha. Okay, sorry, it is would basically we have two values, my mistake, I will just basically do it. So, this will be alpha by 2, this will be alpha by 2. So, this would be f m minus 1 n minus 1, right hand side area is alpha by 2, in this case it is 1 minus alpha by 2. So, in this case we will have basically, I am basically drawing the last one at together. So, now I will basically highlight it accordingly. So, I jumped, but just bear with me. So, if it is of the less than type where H naught, as I mentioned that for H A is the important less than type. So, it will be f m minus 1 n minus 1, this area is alpha, this area is 1 minus alpha. So, this would be 1 minus alpha. So, if it is onto the left hand side, we will reject H naught. So, as usual, I will try to basically highlight the right hand side. So, this is the less than type one. So, let me first erase it, then draw the diagram for the second case which is greater than type. So, this is the area on the right which is alpha, this is the area onto the left 1 minus alpha, this will be f m minus 1 n minus 1, and the area being covered onto the right as per the nomenclature is alpha, rule is also that. So, you will basically reject H naught provided the ratios of the best estimate of the the variances of the population, which are now, I am repeating it, please excuse me, is those are not the S dash, they are the S without the dash, because you have lost 1 degrees of freedom from both population 1 and population 2. So, that ratio should be on the right hand side, and if that is true, then obviously we will reject H naught. Finally, if it is not then equal to type, which I have already drawn, but please, this is the 2f. I will highlight these areas. This is alpha by 2, this is alpha by 2, this area is 1 minus alpha, this is f distribution with m minus 1 and minus 1, area onto the right as per the nomenclature is alpha by 2, which actually will follow the rule. This is f n minus 1, n minus 1, area onto the right is 1 minus alpha by 2, this is the area in between, and basically you can give the rule that if the values of the statistics are in that mod distance, then you will basically reject accordingly. So, the rules are the algorithm how you basically do the problem are exactly the same for each thing, less than type onto the left, right, greater than type onto the right hand side, not equal to obviously on the right or left. But only remember, I am again repeating it, please excuse me for doing that, when it is something to do with the mean, provided standard deviation is known, then you will always use Z, left or right or middle, means not equal to that part. If it is something to do with the mean, the standard deviation is unknown, that you will use the t distribution, and t distribution would have 1 degrees of freedom less. If it is something to do with the differences of the mean, provided the standard deviation of the populations are known, then you will again use the Z distribution, both for the left and for the right as well, not equal to, that means in between. If it is something to do with the differences of the mean, provided the sample variances are unknown, then use the t distribution. But and obviously, in this case you will have a pooled sample variance, standard error, whatever it is. But remember that you would be losing 1 degrees of freedom from the first population and 1 degrees of freedom from the second population. So, if the population, if this the sample size from population 1 is basically m1 and the sample size from the second population is n1. So, in that case the degrees of freedom would be m plus m1 plus n1 minus 2, because you are losing 1 degrees from both. Now, come to the fact that if it is something to do with finding out the actual value, that hypothesis about the mean value, provided the standard deviation of the population is not known, again with repetition I am saying you will use the t distribution with n minus 1 degrees of freedom, and the standard errors of the sample would be utilized at the best estimate. So, those are the set rules. Now, when you come to basically try to find out something to do with the variances, the ratios of the variances, or before that you want to find out something to do the variance from one population, if the mean value of the population is known, you will use the chi-square without losing 1 degrees of freedom for the left hand side, right hand side, in between. But be rest assured that in place of sigma square you will use the best estimate, provided mean value is known, you will use S dash square and do the calculations accordingly. Now, if it is something to do with one population, something to do study with the variance, then be rest assured that if the value of the sample mean is not known, you will use the chi-square with n minus 1 degrees of freedom, that you will lose 1 degrees of freedom is lost, and in place of S dash you will be using S without the dash. Coming to the ratios of the, which we just discussed, coming back to the ratios of the two variances from two populations, population 1 and population 2. Obviously, as the norm is, if it is something to do with these ratios and provided the population mean mu 1 and mu 2 are known, then you will basically immediately use the F distribution with m comma n degrees of freedom, because you are not losing any degrees of freedom, because the population mean values are known. If the population mean values are known, obviously you will use the standard error from the sample, where the standard error would be S dash with the corresponding observation size or sample size. Similarly, for the sample from population 2, you will also use S dash with the corresponding sample value. In this case, we are considering from the first population, we are picking up a sample of size m, and from the second population, we are picking up a sample of size n. Now, when we come to the final stage, final discussion is that something to do with you want to find out something to do with the ratio of the variances, but the ratios of variances, the best estimate would be S without the dash or with the dash. Obviously, it will come out as we discussed, but as you can guess, it would be without the dash. Yes, rightly so, because the population mean mu1 and mu2 are not known. If they are not known, obviously they have to replace when you utilize that standard error to which is the best estimate for sigma square 1 or sigma square 2, that means for population 1 and population 2. When you are using S without the dash, in both the cases you will use 1 degrees of freedom. Hence, the F would basically have m minus 1 and n minus 1 depending on the degrees of freedom which is there for the first for the numerator and denominator. And in case when this is done, obviously this would be true that if you are using for all these cases, I just missed it, I will just recap as at one another bullet point. Then if it is the less than type, then you will use the right hand side of the area of 1 minus alpha and left hand side of the area as alpha. If it is greater than type, the area onto the right hand side would be alpha and the left hand side would be 1 minus alpha. If it is not equal to, basically you will have then 3 regions. Over the upper control limit, it will be alpha by 2, below the lower control limit, it will be alpha by 2, and the in between area obviously would be 1 minus alpha, which is the level of significance. Now, we will consider the concept of linear regression, and so consider a background for the problem. So, consider that in the case of linear regression, you have some set of variables which are to be utilized for prediction, and there is one variable, consider that as y, which is to be predicted or forecasted, whatever. And we will assume that these variables which are to be used for forecasting have some properties. I will consider those properties in details further on. So, our main concept in regression will we want to basically regress on the past data. So, the past data can be depending on, say for example, I want to find out the oil price. So, oil price would definitely depend on the GDP, the GNP, what is the dollar to rupee rate. I am finding the oil price which relevant to India. So, it would be dollar to rupee rate, then euro to rupee rate, what is the inflation rate, and all these things. So, obviously, we will have all these variables which will be utilized to predict the oil price would be considered as independent variables, and the one which you want to predict or forecast would be called the dependent variables. So, and obviously, the relationship between the independent and independent variables will continue, and we will discuss that soon. So, in multiple linear regression, there would not be any randomness in measuring x. So, what are these x? X's are those variables which will be utilized, and they are the independent variables. So, we will consider there is no randomness in measuring xi's. So, consider there are x1, x2, x3, x4 till xk number of such random variables which are there. The relationship is linear and not non-linear. So, obviously, in this case we will consider as the word is multiple linear regression, we will consider the relationship between the x's or x1, x2, x3, x4 whatever they are the independent variables, and their effect on the dependent variable which will be mentioned as y is basically linear in structure. By nonlinear we mean that at least one derivative of y with respect to the beta. So, what are the betas? Let me explain. So, consider that you have a regression where y is dependent on some alpha which is a fixed value. So, this fixed value will have some significance, I am going to come to that later on. Alpha plus beta 1 x1 plus beta 2 x2 so on and so forth till beta k xk, considering there are k number of random variables plus some epsilon which is an error. So, this technically betas beta 1, beta 2, beta 3 till beta k very simply would mean that keeping all the other variables constant. If I am only concentrating on the first variable, then beta 1 would basically give me the rate of change or the rate at which the function y would be changing for 1 unit increase in x 1, keeping other things fixed. In a similar way, when I considering beta 2 or beta 3 or beta 4, consider that I am considering beta I, where I is equal to 1 to k, we will consider that in that case beta I would be the rate of change of the y function with respect to x I, provided others are fixed. Now, in this case the alpha which I mentioned, I will draw this diagram in later in details. When I am considering this alpha, alpha basically means the coordinate at the value at which it cuts the y axis. So, if you in school, if you remember, we have done the equation y is equal to mx plus c, where m is basically the slope, x is the variable based on which you want to predict y, and the c value is basically where the straight line is basically connecting the value of y axis where the x value is 0. Now, whenever you are trying to basically consider that, obviously that epsilon which I mentioned is basically the white noise. So, obviously white noise is there, randomness is there, and this randomness would basically have some distribution. In general, we consider the randomness has a distribution which is basically normally distributed with a certain mean and a certain variance. In the simplistic case, we consider the randomness or the white noise or the error to be there, which has a 0 mean value and one standard deviation of variance, which is basically the standard normal deviate. But obviously, you can change the variances accordingly, but technically we will always consider the expected value to be 0. So, let me continue reading it. There is no randomness in measuring exercise. The relationship in linear and non-linear is linear and not non-linear, but non-linear we mean that at least one derivative of y with respect to beta is a function of at least one of the parameters. By parameters we mean basically the betas. So, this slide I will consider in more detail, because considering the 30 minutes for this class are almost over. I will discuss that, but again in the next class also I will start from the same slide. So, do not, because in general whatever slide I take up, I generally wrap it up before the end of the class, but this would be need more discussion. So, we will consider that in the next class also. So, assumptions for the multiple linear regression model. So, here we will have x1, x1, 2, 3, 4 whatever, y's are normally distributed. I am just reading it, I will come to the significance later on. Xi's are non-stochastic as I mentioned. The error term which I mentioned is basically normal, 0 mean, and this is given as sigma square I, but I will consider very simply that they have a variance of 1. The rank of this matrix is k, that means rank, if you remember, is basically the linear dependence of the rows and columns which is there for the matrix. Where it is coming, I will go to that, but k, remember, is the number of independent variables which are there, and obviously n, the number of readings based on which you will try to basically predict for the nth plus reading is greater than equal to k. And this is also another significance, because if you are solving some linear equation, it would mean that the number of equations should be, if there is all the equations are independent of each other, then the number of equations should be more than the number of variables to be found out, because if it is not that case, then there can be redundancy in the calculations, and obviously we know from simple linear equations which you have studied. So, there would be no dependent structure between x's, that is the rank of the matrix X is basically as given, and obviously it would mean that the dependent structure not being there between x's, it would mean that they are independent on each other. The expected value of the covariances between the errors is 0, that means they are not dependent on each other, and the covariances of the independent variables with the error would also be 0, that means the white noise is by itself a standalone case, it is not going to basically affect the readings of either x1, x2, x3 or xk. I will basically close it here, continue the discussion more about the assumptions, and basically draw the equation in order to basically and highlight how it looks like and what uses the multiple linear regression can have. With this, I will close this class and have a nice day, and thank you very much for your attention.